Let's do it together, guys! Yo!
The STM is the muscle.
Making sure every single move is precise.
The Pi will be the brain.
Its cameras, the eyes that find the runes.
We will build the Nexus map to start the quest.
And send coordinates and show the runes live.
Our logic will find the smartest path instantly.
And it will react to the arrows on the flag.
The Android app connects to the robot via Bluetooth using the connect button, which lists available devices for selection and establishes a robust connection that automatically recovers if interrupted. Once connected, the Send Ops button transmits the current obstacle's coordinate, image facing, and obstacle IDs to the robot for further processing. The Start button then triggers the robot's readiness to undergo the simulation for its assigned tasks. Next, we created an intuitive graphical interface. Users can drag and drop obstacle objects onto the grid, placing them only on empty locations. Tapping an obstacle allows you to change its facing direction, helping you specify the target sites accurately. Similarly, bigger objects can be placed by dragging them onto the grid. When the robot sends over the target ID, the obstacle is automatically replaced with the corresponding target ID on the Android interface. Finally, a reset button clears all obstacle input obtained from the robot, returning everything to its original state and preparing the system for this next test run.
Next is the STM component. What you see here is the different turns running on dual DC motors with PWM and quadrature encoders. This is closed by a PID loop for straight movements, forward and backward. As for turns, we utilize the gyroscope along with a low-pass filter. What is unique here about our robot is the in-place turning of the wheels, achieved by spinning one of the motors forward or having the other motor spin backwards. This ensures a very precise set that you can see here.
For obstacle detection, we mounted a front ultrasonic with low-pass filter and outlier rejection to kill spikes. We also have two IR analog sensors mounted at the side for close range detection and wall following. The RPi sends a command like FR90, which the STM then passes to its UART receive interrupt and executes them by controlling motors, servos, and sensors, and after completion, sends an acknowledgement back to RPi. This modular communication chain keeps computational heavy tasks on the RPi, while the STM focuses on real-time actuation, ensuring smooth, deterministic performance on the robot.
This is the visual representation of the communication between the different devices and the RPi.
An Android tablet serves as a command center connecting to a Raspberry Pi via Bluetooth. The tablet sends obstacles and target information to the Pi which forwards this data to a pathfinding algorithm running on a flash server. The algorithm processes the information, calculates optimal routes, and sends direction commands finally back to the Pi. Finally, the Pi transmits these commands to an STM32 microcontroller via USB serial, which directly controls the robot's motors.
This is a visual representation of how we approach image recognition.
The RPi camera captures real-time video frames as the robot moves. We use the latest YOLO V11 for object detection to recognize given symbols. We collected the data by taking pictures of the symbols given and creating a labeled dataset with it. Then we fine-tune the model with this dataset, and the model is ready for object detection.
This is Gridlanders, a robot with a 2D grid with random brick obstacles. The goal is to reach the target via the shortest, safest path, rerouting instantly when the map changes. We use modified A-star search. Beyond move cost, we add rotational cost as well, where turns aren't free, and a safety buffer for the walls. Start, check neighbors, compute, move, plus turn, plus safety, and choose the lowest, and then repeat. The logic is to generate up, down, left, right, then to compute cost, then generate heuristic equals Manhattan distance plus minimal turns, and finally choose the smallest F.
Here is an example of how our algorithm chooses to move for the following obstacle map. Some of our innovation include, but not limited to, rotation-aware cost, which penalizes unnecessary turns, customizable safety buffer around obstacle, dynamic rerouting to replan an obstacle or update event, better heuristic by using combination of Manhattan and minimal turn lower bound, half smoothing for small post-processing to remove the zigzags while respecting safety, and lastly, fail-safe handling in the case of block goal, tie break by lower H and loop guards.